Hello and welcome to the demo 1 of the Getting Started with µRTE. My name is Thomas Barth and I am the creator of µRTE. It is assumed that you have seen the introduction video of µRTE because in here we will make use of what you have learned in there. For this demo, I will use the plugin version of µRTE, which in this case is now integrated into STM-Cube. I have already imported two projects here. So the first one is the µRTE model or project with the µRTE model, and the second project is the code we want to build. This demo is based on an STM Nucleo F103 board, but because also for other demos the model structure is always the same, this demo can also be used for other targets. Because simply it would take too much time to create entire models now in this video, I've created a set of several projects, and for every project additional features and functionalities are added. In this video now we will start with a template project in which the most basic configuration already is done. We will go through its functionality and its configuration, and then later on we will bring in the next project which now already has some functionality integrated, and we'll discuss how this was realized and how you could possibly extend that and basically how to use the tool. In the first step, I first want to explain the content of the model as it is right now. As mentioned, currently there is no application in it, but it's just a more or less empty template. To make life a little easier, I already have added the hardware in here. As mentioned, this demo project now is for an STM Nucleo board, so the board already is in here with some basic external peripherals on the board, which we will use later on in this series. And most important, there's already the microcontroller described in here, which consists out of an ARM Cortex M3 core, a RAM module, some GPIOs, and UART. So that's already there. The logical function model and the requirement model are entirely empty, so we will focus on the software model. First, I will go through all the elements step by step, and then I will briefly explain how you could start to model an application from this point. Within the application, you could now right-click and create software components and source folders, but for now there's nothing in there because we do not have any application. The RTE is associated with the so-called base protection set. We will later discuss protection sets a little bit more in detail, but the general idea is that you can define a protection set which contains all the resources which should be available throughout the entire system. Typically, things which go in there are the timestamp source, error handling mechanisms, and so forth. So, but you should be aware that everything which is in there is accessible by everybody from everywhere. The activation engine object, the properties which we can find directly in here, are the it's basically the configuration for the system task. So we define on which task or on which core this system task, the so-called central activation engine CAE, is executed. We define where the global data of the runtime environment shall be stored. So this is basically, for example, the current system state, meta information on where to find application tasks and so forth, where this is located, and we need to define also a stack for this central activation engine. Within the signal layer, there currently is nothing because we do not have any signals and no application. We need to at least define one system state, and we have to define what should be the initial state when the system starts, which in this case simply is the only state that has been defined here. RTOS in here, we later on will have our tasks, but for now this is empty. For linkage, the properties here are the MPU alignment. So if later on the linker description files are generated, then this alignment as it is defined here will be inserted into the linker description file, but because of certain MPU requirements and other constraints, all that is generated as user code, so that it can later on be modified. The linkage strategy defines how the metadata of µRTE is linked into memory and how the memory protection boundaries are configured. In monoblock linkage mode, all the global RTE data is put into a single memory block. The central activation engine, so the system task, has read-write access to everything except the runnable monitoring, while the task activation engines, the TAEs, they have access to this entire block. The advantage of this linkage mode is that the system task as well as the task activation engines or the tasks only need a single entry for the MPU configuration for the RTE, which can be very handy if you have constraints in your hardware or in your operating system, if you simply have not that many slots for your memory protection. However, there is no memory separation at all, and all states can be read and modified also from the runnable context. So if a runnable, for example, for some reason would be aware of the address of the system state, then it could simply change that because there is no memory protection in place. In separated block linkage mode, all the global RTE data is again put into a single memory block, and the central activation engine has read-write access to everything, to the entire block. But the task activation engines, they now have two sets. One is read-only for the system state, for the global live monitoring, and they only have write access to their own record. So the idea here is the central activation engine only requires one MPU entry, but in this case now the task activation engines require two. As a side effect here, the central activation engine has full access to all of the task activation engine data. In separated protection block linkage mode, all the global RTE data again is put into a single memory block. This time also the central activation engine requires two entries. It needs read and write access to its own the data it is managing, so the mainly the system state, the live monitoring, but it only requires read access for the meta information of the tasks, while the tasks now require three entries, so they need read only for the system state and the live monitoring. For the live monitor, which is the record for that particular task, they need read and write access, and for their own metadata, they again need read and write access. So in total, 3 entries per task. In separated linkage mode, the central activation engine as well as the task activation engines have individual memory blocks for their global RTE data, and the central activation engine has read and write access to the system state and its own alive monitor, as well as read access to all of the task activation engine's data. The task activation engines have read access to the central activation engine data and read and write access to their own records, so alive monitoring, state, runnable monitoring. And while the central activation engine requires one MPU entry plus 1 per task, the task activation engine requires 3. So in this linkage mode, the number of entries for the central activation engine rises with the number of tasks being managed. In the output sections area, we now have 2 output sections modeled. One is for the global RTE data. So this one is the one we referenced here in the activation engine. And the other output section is the output section for the central activation stack. For now, we also only have one protection set, which is the base protection set. As already mentioned before, this is the protection set which should contain all the resources that needs to be accessible in every context. So typically, as I said, timestamp sources, error handling, logging, things like that. And this base protection set is what was referenced from the RTE. The last entry are the data types, and as there is no application, there are no data types defined. This is the end of demo 1, and in the next demo I will show how to fill the model with data and how to use also the graphical representation. Have a nice day. Bye.